Hello, everybody. So, we are working with probability and statistics in this section. If you remember on Friday and Thursday, we were working with permutations and combinations, which just tell us the number of ways an event can occur. That's going to kind of come in handy today when we're working with finding probabilities of certain events. Now we're going to work with finding theoretical probabilities, experimental, and using simulation to represent certain situations. Okay, now a lot of this stuff was going to be kind of demonstrations or have you guys worked out in class, so I'm going to have to do some of these on my own. But we'll start with this definition of experimental probability. And the experimental probability of an event, and a lot of times you'll see the probability of an event in parentheses, whatever the event is, well, that's given by taking the number, I don't want to write in that color, taking the number of event occurrences, the number of times that event occurs, over the total number of trials. Okay, that's an experimental probability. So, one example we were going to do is this next one. What is the experimental probability, if we look in the parking lot, that a vehicle in the lot is a pickup truck? So I'll look out my window, look down the street, and I currently see two vehicles down my street. I see two vehicles. Well, of those vehicles, one is a pickup truck, actually. So the experimental probability that a vehicle is a pickup truck is, well, how many in quote unquote, you're going to have to think about the number of trials as, well, how many things or how many vehicles are there? Well, there's two vehicles, the number of trials is 2, and how many of those are pickups? Well, the probability experimentally of a truck, pickup truck, is given as 1/2. Apparently, the experimental probability of me looking out my window and seeing a pickup truck is, well, 50% of the pickups, or 50% of the cars are trucks. So an experimental probability, we're going to talk about theoretical later. Experimental is you do the actual thing, and what is the likelihood that an event occurs is given by taking the number of times that event occurs, or excuse me, it's the probability that that's going to occur is the number of the event occurrences over the total number of trials. Okay, so at your table, you are going to roll a dice 10 times and record how many times you roll a 3, and then the total number of times you rolled, and then we were all going to add those together and find the experimental probability of the entire class of rolling a 3. But I'm just going to use a simulator online. So the probability of rolling a 3, well, let's say that you all, you had groups, so maybe 8 groups. Let's round that up to 10 groups, and you rolled it 10 times. So let's do, 100? I'm going to narrow that down. Let's just do 40 total rolls first. So we're going to roll a dice 40 total times, and we want to know how many times we roll a 3. And I would encourage you, we haven't talked about theoretical probability. See if you can find the theoretical probability. We'll talk about that later. But see if you can find the theoretical probability and see if it's close to this probability I get here. So I'm going to roll a dice 40 times, and we're going to count the number of times that I get a 3. So I'm rolling dice, and this is a 6-sided dice. How many times do I get 3 out of 40? Well, I get it once here, twice, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. I get it 13 times. So the probability, well, what were the total number of trials? There were 40 trials where we rolled 40 dice, and of those 40 trials, 13 resulted in a 3. So our probability is 13 over 40, which is, well, can I simplify that, or is there anything that goes into 13 that goes into 40? And the answer is no, because 13 is prime. But if you plug that into your calculator, that as a decimal is approximately going to be 13 divided by 40. It's about, or it is exactly, 0.325, which is 32.5%. Now, if you found the theoretical probability of rolling a 3 on a dice, and I guess we can find this easy enough before we even talk about theoretical probability. The theoretical probability of getting one number on a 6-sided dice, it's similar to finding theoretical probability. How many outcomes are there on a dice? There's 6 outcomes. Of those 6 outcomes, how many result in a 3? 1. So really there should be a 1 in 6 chance, which is actually 16%, which is not very close to our theoretical probability. However, what's going to happen in experimental probability the more times we do that experiment? And this might be something you're familiar with doing probability in the first place. Like the probability of flipping a coin and getting heads or tails is, well, it's 50% in each case. But if you, for some reason, did 3 trials and you got all heads, your probability of getting tails then would be 0%. But does that make sense? You know it should be 50%. So really, the more trials you do, the more accurate your probability is going to be. So if I simulated using 100 dice, I should probably get a better number than 32.5, not guaranteed. Or I should get a number closer to 16%. If I do 1,000 trials, I'll probably get more accurate. The greater number of trials, the more accurate your experiment is going to be. And that's the reason in experiments in general, you need to do more experiments to get more accurate results. So you can kind of, I guess you can't prove your hypothesis, but you can more strongly support your hypothesis that this is going to happen if I do it more than likely. All right, so keep that in mind. Experimental probability, it's not exact. It's not going to give you the exact probability of something that should happen, but the more trials you do, the more accurate it should be. Okay, so how many possible outcomes are there for one roll? We already kind of talked about this up here. This is theoretical probability, which we'll talk about in a little bit. Okay, but there are 6 total outcomes for one roll. Now we're going to talk about theoretical probability here now. A sample space is just a set of all possible outcomes in an experiment. It's a set of all possible outcomes in an experiment. I butchered that. That's all right. Okay, now equally likely outcomes, it describes itself. It's just outcomes that are equally likely to occur. Outcomes that are equally likely to occur. So, rolling a dice, every single outcome is equally likely to occur. You're as equally likely to get a 1 as you are a 2, so on and so forth, unless the dice are loaded. So, all outcomes are equally likely to occur there. That's an example. So, theoretical probability, it's found very similar to experimental probability. If a sample space has n equally likely outcomes, basically n is the total number of outcomes, and an event A occurs in m of those outcomes, then the theoretical probability of event A is equal to taking that number of outcomes, m, and dividing it by the total number of possible outcomes, n. So, for example, we were up working with this probability. Well, how many outcomes are there on rolling 1 dice? Well, there's 6 total outcomes on 1 dice, and one of them gives us a 3. So the theoretical probability is 1/6. That's a theoretical probability. Okay? So, we want to know, what is the theoretical probability of getting a sum of 5 on one roll of 2 standard number cubes? Okay, that just means dice. Now we have to think about our outcomes here. Technically, we have 2 dice. I'll do blue and I'll do red here. Now this has how many outcomes? This blue dice has, if it's a 6-sided die, if it's a cube, it has 6 outcomes. This one has how many outcomes? This has another 6. So how many total outcomes are there? And before you answer that question, let's make a table. This is always kind of helpful for these types of problems. We want to know the theoretical probability of getting a sum of 5 on one roll of 2 standard number cubes. Okay, well, if we're finding theoretical probability, we need the total number of possible outcomes, and we need the number of, well, the ways this event can occur. So let's make a list here. I know that for this blue die, I can either get a 1, 2, 3, 4, 5, or a 6. For this red die, I can also get either a 1. I guess I'm going to write smaller to give myself some room. I could get a 1, 2, 3, 4, 5, or a 6. Okay, so the total number of outcomes You might be kind of seeing it more clearly now. Okay, well, I'll just do this I could get a, oh, whoops, I need another line here. I could get a 1 and a 1, that's a sum of 2. And I'll label this chart. I could get a 1 and 1, that's a sum of 2, 1 and 2, that's a sum of 3, 1 and 3, that's a sum of 4, 1 and 4, that's a sum of 5. Okay, and I'm not going to fill out this entire chart. But if I have 6 columns and I have 6 rows representing the outcomes, how many outcomes are there? And the answer is 36. Okay, so we know that our probability, I'm running out of colors here, let's do probability for sum of 5 is given by number, if you go back to your theoretical probability definition, it's given by taking the number of, well, outcomes, number of ways that a sum of 5 can occur. I'm going to erase these die, we don't need these anymore. Number of ways the sum can occur over the total number of ways or the total number of outcomes. Total number of outcomes. Total number of outcomes. Okay, well, if there's a 6-sided dice being combined with a 6-sided dice, there's going to be 36 total outcomes. 6 times 6 is 36 total outcomes. Of those outcomes, how many give me a sum of 5? And that's where the table might come in handy. 1 plus 5, if I get a 1 on the red die and a 4 on the blue die, that gives me 5. If I get a 1 on the blue die and a 4 on the red die, that gives me 5. If I get 3 on the red die and 2 on the blue die, that gives me 5. And if I get 2 on the red die and 3 on the blue die, that gives me 5. So if you notice, this kind of makes a diagonal here. Are there any other things that will give me a sum of 5? And the answer is no. So how many ways can we get a 5 then? Well, if we have this combination, that's 1 way. That's 2 ways, 3 ways. There's 4 ways over 36. So 4 over 36 ways is the probability of sum 5. Well, 4 over 36, that's the same as, can you reduce those? Yeah, divide by 4, that's the same as 1/9, which if you plug that into your calculator as a decimal, you should get approximately 0.11 repeating, or move the decimal 2 places to the right, that's the same as 11.1%. So there's an 11.1% chance that you roll 2 dice and get a sum of 5. So remember, for theoretical probability, you just want to find the number of ways that that can occur over the total number of possible outcomes. All right, we're going to talk about simulation then. We want to roll 2 dice using the dice simulator, see if we get a sum of 5. Okay. So simulation is basically what I was using before. It's just doing something instead of actually performing the experiment, kind of like instead of me actually rolling a dice 40 times, I just simulate that using, well, something. And we're going to see a not so easily translated example here. But I'm going to roll 2 dice, and I want to see, well, am I going to get a sum of 5? Roll these 2 dice. I got a 2 and a 4, which is 6, so no. We know that my theoretical probability of that happening is an 11% chance. Now, the more I roll this, the more likely, and I record all my observations and then the total number of trials I do. This was 1 trial. And I record the number of trials and put that in the bottom, and the number of successes in the numerator, the number of successes being how many times I got a sum of 5. If I do that more times, I should get, well, close to 11%. If I did like 1,000 trials, it'd probably be pretty close. But keep in mind, for these experimental and, I guess, simulation methods, the more trials you do, the more accurate it will be. Okay, so we're going to go back to our notes here. Simulation, we're going to talk about that. It's just a way to model events a way to model random events such that simulated outcomes closely match real-world outcomes. Okay, now, just like experimental, if you only use a few simulations or a few experiments, your probability is not going to be incredibly accurate. So the more simulations you use, the more accurate it should be. So we want to simulate, what is, this should say simulated probability. Okay, so on a multiple choice test, each item has 4 choices, but only one choice is correct. That's just like any multiple choice test. How can you simulate guessing the answers? And we want to know, what is the simulated probability that you will pass the test by guessing at least 6 of the 10 answers correctly? What is the simulated probability that you will pass the test by guessing at least 6 of the answers correctly? Okay, so here's what we're going to do. We obviously can't do an experiment right now. I mean, maybe we could if we all had you take a test. But to kind of speed the process up, we're just going to say we're going to simulate this event. And we're going to, well, we need to know a couple things. If each problem has 4 choices and one is a correct answer, we're going to assume that this is a randomly assigned correct answer. Well, the probability of getting one answer correct is 0.25, right? 1 in 4, or 25%. Okay, so that's the probability of getting 1 correct. Now, the way of guessing and getting 6 of the 10 correctly exactly is a little bit more complex than what we're prepared for right now. So we're going to find the simulated probability. But first we need to figure out how we can simulate guessing the answers. Okay, well, if there's a 10-question test, what we can do here is we can just generate 10 integers that represent our 10 problems, and we're going to let the integers that we generate be from 1 to 4 to simulate the questions. And we're just going to assign a correct value to one of those integers. It could be any one you choose. So we're going to generate a random integer from 1 to 4, and that's going to represent a single question. So I could, if I just did it once, let's say question 1 and I got 3, okay, that would be like choosing C maybe, okay? But instead of, I guess, aligning it to A, B, or C, we're just going to let one of those numbers represent a correct solution. Since your number generator has a 25% chance of generating a number, if we're saying it has a 25% chance of generating a 1, a 2, or a 3, or a 4, well, that's the same as the probability of getting that answer correct. So we'll just say, well, let 2 represent the correct answer. We'll let 2 represent the correct answer. So just to kind of build here, and then we'll talk about how we can represent this entire quiz. If I generate, not what I want, here we go. If I generate 1 random integer, just to represent 1 question, and its integer should have a value between 1 and 4, well, we said, I actually forgot, what did we say, 2? Yeah. We said 2 is going to be the correct answer. So if I get a 2 here when I generate this number, that means I got a correct answer. Okay, I got a 3, which means that we got the wrong answer on that one. So what we're going to do is generate 10 integers to represent the 10 questions. Each integer is going to value 1 through 4, and we're going to count the number of times we got a 2. Okay, so here's my 10 questions, here's my 10 answers. The experimental, or I guess the simulated probability that we got a correct answer is, well, we got 1 correct answer here. We got another correct answer. So we only got 2 out of 10, which is equal to 20% chance, right? So that was the experimental probability of getting a correct answer. We know that it should be what? It should only be about 25%. That's actually pretty close. And what's going to happen the more I do this experiment? Like, let's say I did it 1,000 times. To represent, well, I guess if there's 10 questions per quiz, doing it 1,000 times or generating 1,000 answers would be just 1,000 divided by 10. That'd be like doing 100 quizzes. So if I do 100 quizzes, I should get something that's pretty close to 25%. Let's see what happens. Do 1,000 random integers from 1 to 4. We're going to format that in 100 columns to represent the 100 quizzes. Okay, now I'm not going to look through these all. I'm just going to use my control find function, count the number of 2's. And I'm going to exclude 1, 2, 3, 4, those 4. So it's 264 minus 4, that's 260 times over 1,000. 260 times over 1,000. And that's going to be, well, you divide that by 100, that's the same as 26 over 100, or 26%, which is even closer to 25%. So on, and if I generate even more numbers, something else is going to happen. So if I did 10,000 and I generated that in 1,000 columns, find my probability here, control find the number of 2's, maybe. I don't know why it's not working. But we should, my point here is you should get more accurate probabilities for those things. So what is a simulated probability that you will pass the test by guessing at least 6 of 10 answers correctly? That's not going to be a super accurate number. What I was planning on doing was having you guys each individually do it, see how many times we got 6 out of 10, which would have been very, very few. But really, getting at least 6 of the 10 answers correctly, it's going to be a very, very slim chance. We're not quite ready as of yet to find that probability theoretically. So we'll kind of ignore that for the time being. Really, the key thing I wanted to talk about here is how we find these probabilities by simulating them. It's easy to do that when you're thinking of dice and things like that using random generators. But for answering questions on a quiz, we kind of had to get a little creative. We had to say the probability of getting an answer correct is 25%, which means 1 in 4. So if I have 4 integers for each problem and let one number represent a correct answer, we can simulate it that way. And you can see that the more times we simulated it, the more accurate it was to what we should have been, how many answers we should get correct. Okay, so I was going to draw from a deck of cards, and then we want to calculate using combinations and permutations. We're going to bring those back into play. But before we do anything, I want to just discuss combinations and permutations. What do those give us? In combinations and permutations, they just give you the total number of outcomes, or the total number of ways that something can occur. Okay? The total number of ways that something can occur. In combinations is the total number of ways something can occur if order doesn't matter. Permutations is the total number of ways an event can occur or something can occur if order does matter. Okay, so we want to draw 5 cards and then calculate using combinations or permutations, and I'm going to just assign a random probability depending on what we draw. So, we're going to draw 5 cards, calculate using combinations or permutations. We'll come back and discuss that in a little bit. So I'm just going to draw a 5-card hand. So 5 cards from one shuffle deck. I'm going to include every possible thing except for jokers, so there should be 52 cards. I draw those cards. So I randomly draw 5 cards, and I got, what do I want to do here? I got 3 face cards and 2 non-face cards. That's what I'm going to say. So, draw 5 cards. What is, and we're going to go back to theoretical probability. What is the probability of drawing 3 face cards and 2 non-face cards. Okay, what is the probability of drawing 3 face cards and 2 non-face cards? So we'll do probability 3 face cards. Okay, and you know that for theoretical probability, the definition of theoretical probability, well, what goes in the denominator is just the number of total possible outcomes. And what goes in the numerator is the total number of successful outcomes, or I guess the number, it's the number of ways, well, I guess the number of ways we can have this event occur, or the number of ways we can get 3 face cards and 2 non-face cards. All right, so the way you find the number of total possible outcomes, we're going to have to use combinations or permutations here. And which is it going to be? So I'm drawing a deck. I'm drawing from a deck, and I have 5 cards. So I guess in this specific instance, I drew 5 cards. I had a queen, a king, a 10, a 2, and a jack. Would that not be the same as having a queen, a king, a jack, a 2, and then a 10? Does the order that I have these cards in my hand matter? And the answer is no, which means this should be a permutation or a combination. And the answer is a combination. So if we want to find the total number of possible outcomes, or the number of total possible outcomes, well, how many cards are in a deck? There's 52. We know that order does not matter. So it's like we're taking 52 cards and we're choosing 5 of them. The order doesn't matter, so we don't want repeated hands that are in a different order because it does not matter. So we're going to do 5 combinations, or 5 choose 2, or 52 choose 5. Goodness. So we have 52 cards to choose from. We're choosing 5 of them. Order doesn't matter, so we're doing a combination. 52 choose 5. Okay? Or we know that 52 choose 5 as a combination is the same as doing 52 factorial over 52 factorial over, well, r minus this value, 52 minus 5, factorial times this value, factorial times 5, factorial. Okay, now what's going to go in the numerator? This is where we have to get creative. We want to think of how many ways can we get 3 face cards? How many ways can we get 3 face cards? And the answer is, well, how many face cards are there? We know that Jack, King, and Queen is a face card. There's 3 in each suit. There's a total of 4 suits, so 3 times 4 gives me 12. So the probability, I guess we'll do this in red, number of ways we can get 3 face cards is, well, we have 12 face cards to choose from. And another way of writing 52 choose 5 in a less confusing way would be to do 52 choose 5 like this. Okay, so the number of ways we can get 3 face cards is, well, if there's 12 face cards in a deck, we want to choose any 3 of them. Okay, now we want to add that. Remember, this gives us the total number of ways that we can get 3 face cards from 12. We have 12 face cards to choose from. We're choosing 3 of them. What is the probability we get 2 non-face cards? And this is where we have to get creative. How many non-face cards are there? Well, if there's 12 face cards in a 52 card deck, how many non-face cards are there? Well, that should be 52 minus 12. That would be 40, right? There should be 40 cards to choose from. We want just 2 of them. Again, order doesn't matter. We're going to do 40 choose 2. And really, we can plug this into our Desmos calculator if we wanted and find this probability. So let's actually do that. We can write these out. I guess this would be the same as 12 factorial over 12 minus 3 factorial, in parentheses 3 factorial, plus 40 choose 2 would be 40 factorial over 40 minus 2 factorial times 2 factorial. Okay, so let's go ahead and plug these into our calculator. If you plug these into Desmos, I'm just going to use my calculator itself. Combinations, 12 choose 3, should be 220. I want to double check that we set our math up right. So this should be 220 plus, I'm going to double check if we do this, 12 factorial, factorial over 12 minus 3 gives me 9 factorial times 3 factorial. Double check, we get 220, we're good there. All right. If we do 40 choose 2 or 40 chosen 2 at a time, that's a combination. Plug that into your calculator. Using Desmos, that'd be fine too. 40 choose 2, we get 780. That's how many ways we can get. This numerator represents the number of ways we can get 3 face cards and 2 non-face cards over the total number of outcomes. So 52 choose 5. And the total number of outcomes is 2, 5, 9, 8, 9, 6, 0. So 2,598,960 ways. Simplify our numerator, 220 plus 780, we get 1,000 over 2,598,960. I don't really care about simplifying that, just plug that into your calculator. 1,000 divided by, and get our probability, 2,598. Should get about 0.00385, which as a probability is 0.0385% chance. There is that percent chance that you get 3 face cards. So what we did was actually pretty uncommon. That's your percent chance of getting 3 face cards in a 52 card deck. Pretty unique hand there, seemingly. Okay. So our last thing we want to talk about is geometric probability. So 2 friends, Maria and Trevor, are playing basketball. They're playing basketball. Okay. Now Maria decides she's going to dunk on Trevor. She has mad hops, so she can dunk anywhere inside this orange rectangle with the labeled dimensions. If Trevor's positioning inside this orange rectangle, the paint, is completely random, which might not be far off because he's terrible at defense, what is the probability he is standing inside that blue area when Maria dunks over him? So this isn't a great example, I guess, in the real world of geometric probability, but it'll work well enough for our cases. So we're basically saying, well, what is the probability that he's going to be in that blue area out of the total orange area? Okay, in the if you want to remember the definition of probability, it's just like having the favorable outcomes over the total outcomes. Okay, well, we have to kind of define what we mean here by total outcomes. Well, total outcomes is, I guess favorable outcomes is, well, what's the likely, our favorable outcome is the blue area, right? And the total outcome is that total orange area. So what we can do for geometric probabilities, it's basically like taking the desired area, finding the probability that something occurs in this spot is like taking the probability, it's like taking that desired area and then dividing it by the total area it could occur in. It's like taking the area you want it to happen in and then over the total area it could occur in. That's similar to theoretical probability. It's like having your total outcomes, or your total area would represent your total outcomes, and then your desirable outcomes, or the desired area we want to be in. Okay, so this is just going to be, well, what's the probability that he's in the orange circle or the orange rectangle? Well, assuming they're in the paint the whole time, it's going to be 100%. I don't know if I actually have an orange marker. Let's change this one to orange. There we go. So the total area, well, if this is a rectangle, we know it's going to be 19 feet times 12 feet. 19 times 12. And then we know that this blue area is going to be 6 times 6, which is 36. So the probability that he's inside that rectangle, well, we take our desired area over our total area. It's going to be 6 times 6 over 19 times 12. So, well, 36 over 19 times 12 gives me 228, which is about, plug that into your calculator, you get about 0.1579 or 15.79%. Okay, so there is, assuming that he is completely randomly standing in this rectangle when Maria decides to dunk on him, there's a 15% chance. Okay, one of the common uses of geometric probability is like throwing things at a dartboard. So if you're throwing things, like if you pretended that this rectangular region was a dartboard, the question might be, well, if you're randomly throwing a dart with zero aim and it is to hit this orange rectangle here, what is the probability it hits this small blue rectangle? Or small blue, I guess that'd be a square. What's the probability you hit this square? And it'd be the same thing. You take your desired area over the total area. And that'll give you your geometric probability. So it's pretty similar to theoretical probability. All right, that is all we're going to cover today. I will see you tomorrow. Have a good day. And as always, stay safe out there.